Hello and welcome to MyScience Tutorials. In today's video we are going to be looking at Kirchoff's law and then how to use Kirchoff's law in calculating in solving practical examples of an electrical circuit. So without wasting much time, let's get started. Now Kirchoff has two laws that we normally use in direct current, that is calculating the amount of current that flows through a circuit when we have multiple resistors and then multiple source of EMF or our applied potential. Now the first law, which is which is normally called the conservation of energy, the law of what? Conservation of charge, conservation of charge. Okay, this law states that the sum of currents arriving at a junction in an electrical network is equal to what? The sum of the current leaving the junction, or the algebraic sum of currents at a junction of a circuit is zero. What do we mean by this? Okay, so the law is telling us what? The sum of current arriving at a junction is equal to what? The sum of the current leaving the junction. So we have an electrical network in this form. Let's say we have wires connected this way. Okay, so the wire came down like this and then it has been split, it has been divided into two. Okay, so this is the junction that we are talking about. Okay, so this is our junction. Let me use another color for that. So this point, okay, is what we are calling the junction. Okay, so when we have current I coming over here, okay, then we have I1 leaving in this direction and then we have what? I2 leaving in this direction. Okay, what Kirchoff wants to tell us in the first law is what? The sum of the current arriving at the junction, that is, if you see the arrow, it means this current is now arriving at this junction. Okay, so the sum of the current arriving at the junction, which is I, should be equal to what? The sum of the currents leaving the junction. Okay, so this is the junction, so the currents leaving the junction in this example are what? I1 and I2. So this means I1 plus I2 should be equal to what? I, which is the current arriving at this junction, which means the current arriving over here will be split into two, not two equal parts. Okay, that doesn't mean if we have, let's say, 4 amperes coming here, 2 amperes will move this way and then 2 amperes will move this way. No, that is not the case. Okay, so we may have 4 amperes arriving at the junction over here, but then we may have 0.5 amperes passing this way and then 3.5 amperes going this way. Okay, it is not fixed. Okay, so never say it is the sum of current arriving, okay, is equal to what? Half the sum of the current leaving. No, that is not the case. Okay, now the second one is telling us what? The algebraic sum of the current at a junction is equal to what? Zero. Okay, so which means if we rewrite this very well, okay, so I, then if we bring this to the other side of the equal to sign, we have minus into bracket what? I1 plus I2 is equal to what? Zero, which means the current at this particular junction is zero because the one that is arriving is the one that is being split into two. So at this junction there is no current at all, or the current arriving is equal to what? The sum of the currents leaving that particular junction. So this is what the first law of Kirchoff is telling us, which is what we call what? The conservation of charge law. Now the second law of Kirchoff so the second law is what? The law that is not conservation of charge. All right, let me just get rid of everything here. Okay, so the second law of Kirchoff is telling us what? It states that in a closed loop of electrical network, the algebraic sum of the what? EMFs is equal to the algebraic sum of the potential difference. Okay, let me take that again. It states that what? In a closed loop of an electrical network, the algebraic sum of the EMFs is equal to the algebraic sum of the potential differences. So it means when we have a closed loop, this only applies to closed loops. So if we have closed loops in this way, okay, then we have our source of EMF over here, then we have our resistors connected over here, another resistor over here, then we have another one over here. So this is resistor 1 R1, this is resistor 3, this is resistor 2. Let's name here A, B, C, and D. Alright, so Kirchoff is telling us, okay, what is trying to say in this second one is that the total EMF over here, so the EMF over here, okay, is the sum of the various potential differences over these resistors or loads over here, which means that when the EMFs, the I, okay, when the EMFs moves from here and it comes over here, okay, the potential difference over here will be different from the potential difference on this resistor, which will also be different from the potential difference we have over here. Okay, so it means the EMF, the overall EMF is what? The sum of the potential difference 1 over here plus the potential difference 2, the second potential difference, which is this, okay, then plus the third potential difference. So if we add the various potential differences over across these loads, which are the 3 resistors we have over here, that should give us the overall sum of the EMF that we have. And then what is the potential difference that we are talking about over? This is simply just the product of what? Current times resistance, or what? Volt. Okay, so it means when this current pass through this particular one, okay, we multiply the current and then the resistance, then we get the potential difference over this load. Then the current that will pass through here, we multiply that current with the resistor 3, then we get the potential difference on resistor 3. The same way, the current that will pass through this resistor 2, we multiply the current and then the resistance of this resistor 2, then we get the potential difference 2. So once we add all these potential differences, we should get the EMF of the cell. Now if this is what Kirchoff is telling us, let's have a look at a practical example of how to use these 2 laws to solve a problem on Kirchoff's law. Okay, so let me quickly draw a diagram over here. I know this is very ugly, but let's just manage it. Okay, so we have 4 volts over here. Then at this side we have 2 volts over here. We have this resistor, okay, 1 ohms. We have another resistor, 5 ohms, and we have this one, 3 ohms over here. Then luckily for us, they are telling us I is over here, okay, and we have I1 moving in this direction, then we have I2 moving in this direction, okay, and then they are labeling here A, B, C, D, E, and then F. Okay, so the question is telling us to calculate the current. Okay, 1, find the current I in this example, and then 2, the potential difference. Okay, the potential difference across what? B, E. So this is the question that we are being given to solve. So before we go on ahead, okay, let's define some terms. So let's say let what? E1 be equal to what? The 2 volts. Okay, so we are saying EMF1 should mean the EMF that we are having over here. Okay, so E2 should be equal to what? 4 volts. Then let's say R1 should be equal to the resistor 1 over here, which is the 1 ohm resistor. Then we are saying what? R2 should be the 5 ohm resistor we have over here, 5 ohms. Then R3 sorry, R3 should be what? The 3 ohm resistor that we have over here. Now if that is the case, you also need to take note of the fact that what the sum of the current arriving at this junction, okay, the current passing through this resistor arriving at this junction is being split into 2 over here. So we have what? I is equal to what? I1 plus I2. Let's name this equation 1. This is really important. So now that we have that, let's look at how to solve this problem. So let's consider loop A, B, E, F, A. So we have A, B, E, F, A. That is A, B, E, F, A. That is a closed loop. Okay. So in a closed loop, we are saying what? The EMF is equal to what? The sum of the potential differences. Okay, like I said. So the potential difference across this particular 2 resistors is what we are going to add. So in this example, the potential difference across the 5 ohm resistor over here is what? Is I times what? 5. Okay, that is current times the resistance, okay, to give us the potential difference. Plus we can see that the I1 is the current that will go and pass through the 1 ohm resistor, not the I, because the I is starting from here. Okay, so it's flowing through the 5 ohm resistor. Okay, so it means the I1 will now flow through what? The 1 ohm resistor. Now the EMF that we have in this closed loop, that is A, B, E, F, A, is what? 2 volts. So we have 2 is equal to, now the I from equation 1 is telling us what? I1 plus I2. So we have here I1 plus I2, that is for the I, times 5 plus what? I1. Then we now break this down. So we have 5I1 plus what? 5I2 plus I1. So we have 2 is equal to what? 6I1 plus 5I2. Okay, so let's quickly make what? I1 the subject over here. So making I1 the subject, we have what? We send this over to the equal to sign. So we have 2 minus 5I2 then divided by 6 as our equation 2. So this is what we have for our equation 2. Now let's have a look at what we will have for let's consider the second loop and see and get the third equation, so that we can solve them simultaneously and get our answer. So I believe at this point I can get rid of the question and everything over here. So if you've not copied it so far, copy it somewhere, because I'll be taking them off right now in a second. So all right, I hope we are all done copying that. Okay, so I know that is very bad, but then, so if we consider the second loop, okay, considering loop, okay, B, E, D, C, B, okay, which technically, let me draw it something very small. Okay, let me redraw everything so that we can all be on the same page. So we have the 4 volt over here, then we have 2 volt over here, we have 1 ohms over here, we have 5 ohms over here, then we have the 3 ohms over here. So this is A, B, C, D, E, and F. So we have I1, I2, and then we have I. Alright, so considering loop B, E, D, C, B, if we consider this closed loop, the EMF, okay, by the second law, the EMF is equal to what? The potential differences. So the EMF over here is what? 4 is equal to, now the first potential difference will be this one, and then the second potential difference will be this one. So we have what? I times 5 again, then plus, in this second loop, we have the I2 is the current that is flowing through the load over here, or the resistor over here. So we have what? Plus what? Plus 3 into bracket I2. Okay, but then we said earlier on that what? I is equal to what? I1 plus I2. Okay, so that is the equation 1 we had. So let's input it here. So we have 4 is equal to what? I1 plus what? I2 multiplied by 5 plus 3i2. So 4 is going to give us what? This is 5i1 plus 5i2 plus what? 3i2. So 4 will give us what? 8. This is 3i2. So we give us 8i2 plus what? 5i1. This is equation 3. Okay, so if we have all equation 1 and equation 2 written down somewhere, let's now go ahead and input the value of what? I1, which is the equation 2, into equation 3 and see what we will get for our current. So let me get rid of everything over here, including equation 2. Okay, so this is 8i2 plus 5i1. Now putting equation 2 into equation 3, it means we'll be having what? We'll be having 4 is equal to what? 8i2 plus 5 into bracket I1 we had was what? 2 minus 5i2 divided by 6. Okay, so if we use the 5 to multiply everything over here, we get what? 4 is equal to what? 8i2 plus this is 10 minus what? 5 times 5 will give us 25. So 25i2 divided by 6. So let's multiply through with the LCM, which is 6, to get rid of the fraction over here. So 6 times 4 will give us what? 24 is equal to what? 6 times 8 will give us what? 48i2. Now plus 6 times the whole of this fraction will still give us what? 10 minus what? 25i2. So this means we can bring the 10 over here. So we have 24 minus 10 is equal to 48i2 minus 25i2. So this means we have 14 is equal to what? 23i2. So we divide both sides by 23. Okay, so we have our i2 to be equal to what? 0.61 ampere. Okay, so our i2 is what? 0.61 amperes. Now if that holds true, if that is our value for i2, then let's try and get i1 so that we can combine i1 with i2 so that we can get our I, which is what the question is demanding that we find. So from here we know what i1 from the equation number 2 we had i1 is equal to what? 2 minus 5i2 divided by 6. So this means we have 2 minus what? 5 into bracket 0.61 divided by 6, and if we punch this into the calculator, we are going to get negative 0.175. So which means our current I, which is what? I1 plus what? I2 will give us what? 0.61 minus 0.175, and this is giving us what? 0.435. So it means our current I, which is flowing through the circuit over here, which is what the question is asking us to find, is what? 0.435 amperes. Okay, let's include the unit for the current. So it's 0.435 amperes. Now the second aspect of the question is asking us to find the potential difference across what? The potential difference across BE. Now the potential difference across what? B and E, okay, is just the product of the current, which is I, times what? R, which is the resistance over here. Okay, that is the potential difference, okay, across BE. So the potential difference across what? BE is equal to what? The current, which is what we found over here, 0.435, times the resistance, which is 5. So if you multiply this, we are going to get what? 2.175 volts. So this is the potential difference across what? B and E. So yeah guys, this is all I have for you in this video. Thank you so much for watching, and I believe This actually helps you solve more questions on Kirchoff's law and how to tackle problems involving such more complex circuit diagram, unlike the normal ones that we are used to. So thank you so much for watching, and then I'll see you in the next video. Bye bye.